Hello everyone, welcome to the second part of hypothesis testing, which is applied. Now what we intend to do is probably not the boring part, but the most rewarding part, the hypothesis testing chapter. Whatever theories we have gone through, we're just going to apply them in Matlab and in R. And I repeat here again and again that I intend to make these videos whereas a practice as a practice for my own self. I have some knowledge in Matlab and I intend to learn R. I'm not quite learned in R yet, so I'm just gonna compare Matlab with R. That I think that will be a very quick and fast way to learn R, looking into Matlab. So if you are looking into this, maybe you already know Matlab and you are trying to learn R. Okay, so enough talking, let's just get into the stuff. The first problem, the linear regression model. Consider this regression model beta xt plus ut in which explanatory variable x is 1, 2, 4, 5, 8 given to us. The aim to test the null where beta is equal to 1, on alternative beta is not equals 1. Simulate the model. First stage is to simulate the model for t equals 5 observation using parameters beta 1 and variance 4. Estimate the restricted model and unrestricted models and compute the corresponding values of the log likelihood function. Perform a LR test choosing alpha is equal to 0.0055% level of significance as the size of the test and interpret the result. Perform a word test for alpha is equal to 0.005 as the size of the test and interpret the result. Compute the gradient and Hessian of the unrestricted model, but evaluated at restricted estimates that are not. Perform an LM test and then change it for E and F where beta is equal to 0 and beta is equal to 2 instead of beta is equal to 1. Now I'm not going to discuss about interpretation of the results, because what they mean by interpretation of results is that if a wall test and LM test statistics results are smaller, or while the restricted and unrestricted parameter estimates are approximately equal to each other or converge. If not, there is loss of power, which means we might not accept null, we reject null. So basically, if our values are, in case of 0.05, if our wall test, LM test and LR test gives us log likelihood functions less than 0.05, log likelihood function values, or basically the difference with simply just remember as log likelihood function values less than 0.05, we'll reject, otherwise we'll not reject null. That's all. So let's see. First, with Matlab, are we defining any local functions? No, that's the first thing to check. Then comes the maths. First we need to create pass in the random string, as we have already seen. This is clear all CLC. In R we'll write remove object rm list, in first bracket list equals is all equals true. So basically list equal is means we are removing everything from previous estimation, all equals true. Then graphics is also off for the first, if there is anything from before. Then random stream set global stream, not default stream, and instead of these we write set seed 1, 2, 3, 4. We can just put 1, 2 instead of 1, 2, or we can put 1, 2, 3, 4 here. They actually, if you give a fixed seed series or number, then you will continuously get the same random values. That is the objective of this. The kind here is used is Marcena twister in R. Helper function, because we're going to use inverse is automatically given in Matlab but not in R. So inverse function, inverse of putting in a function m, but which returns the solve, which returns solve m. Solve is the inverse of m. The solve, which returns solve m. Just remember that. So what are given to us? T equals, we are putting everything as a function for R. You can do that for Matlab too. That's not something difficult. Just put everything in a function. So given is t is equal to 5, where t is equal to, we can just put t is equal to 5, or because there are 5 observations, t is length of x. So x is equal to 1, 2, 4, 5, 8 transpose, but in R we already get things in columns, so C 1, 2, 4, 5, 6, beta passing 1, sigma passing 1. Then generate the first data, which is mu, the disturbance, and y. Mu is sigma multiplied to, we are generating disturbances with random numbers, t rows 1 column. R norm is random number, same thing. T, we don't have to mention how many columns because it automatically generates for 1 column. Then y equals, it indexes, we are using its index, that's all. Beta x plus mu, that is given to us, beta x plus mu. Constraint estimation, first constraint are restricted and then unrestricted. Constraint beta hat is equal to 0. Remember, in restricted, the parameter that we are estimating will make it null. We make it null, we'll make it 0. We don't want to include that in the final estimation, and then we can actually make the difference. Beta hat means sigma square, with restricted estimation is mean y minus, this is simply y minus beta x by t, y minus well, y bar squared by t, and y bar is equal to beta hat multiplied to x, that's all. Same thing, mean. Then log likelihood function. The log likelihood function is half log twice pi minus half log sigma square minus half into 2 half multiplied to t into sigma square t, summation of y minus x beta hat, summation of y minus x beta hat squared. For each element in R, we don't need to pass in element by element because it automatically does things in elements. So f printf constraint estimator results are put in constraint estimator results. We do cat function, which is concatenate and print beta hat. So simply same obligate things start with obligate. Wow, Matlab also use slice n. So slice n start, and in Matlab we end with that. That's all. Beta hat. First inverted comma, first inverted comma, then comma, same structure. Amazing. First inverted comma, log. So n, that's all. We end with n. Oh, this is just giving us space. Then unrestricted estimation. Now we don't pass beta hat is equal to 0, but rather beta hat is equal to x, y, OLS. This is not divided. You see, this is, I'm not dividing them. This is right division, or the right division. Yeah, this is the right division. You see the difference? This is left division, left slice. This is right slice, means regression. We're running a regression. This is OLS. Okay. See, this is different. Well, it was easy for Matlab. LM is linear model. LM stands for linear modeling. Y is dependent, x is independent. Y to x minus 1. This is the coefficient. See, minus 1, and I'm passing this as the coefficient. Or we can check what is suggested by LM. fitting linear model. You see, we're just putting linear model in formula -1. Okay, we don't need so many stuff. Coefficients -1, and with a dollar sign, coefficient, much difficult than Matlab. With a dollar sign, coefficient COEF. Then error is y minus x beta hat square, as we already know, minus y hat whole square. It is that, and the mean of the error term is sigma square. Log likelihood function remains same, minus of sigma square, assumption y minus exactly the same, you see, because this will turn to 0 with the value that we put in as well. That's all, because previously for constraint sigma square mean y minus error, we didn't need error because beta hat was 0. So we didn't calculate error. No, we could have. This is the error term, you see. We could have, we just didn't do it in 2 lines. Did do it in 2 lines. This can be done in a different way. That's what it is being shown. That's all. We could have done that too. We could have put everything inside sigma square 1. Things could have been much easier. Okay. And then the log likelihood function, they remain the same. No change. The presentation of the log likelihood function remains same. There is no change. Then comes likelihood ratio test. 2t log L naught minus log L1. We have already calculated that. And probability value is, because log likelihood ratio test is asymptotically distributed, okay, because they all converge to all tests. We have studied in the hypothesis testing chapter. So probability value is 1 minus chi-square distribution function, chi-square distribution of LR by 1. Let's see, chi-square CDF. Let's see if there's something we can find. So chi-square cumulative distribution function, CDF xv computes the chi-square CDF at each of the values in x using the corresponding degrees of freedom. V is degrees of freedom. We can be vectors, matrices, or multidimensional arrays. And this is the gamma function that we will use for degrees of freedom in later examples. Well, tau is the gamma function. Just need to remember that for now. So that's chi-square. This is 1 degrees of freedom. So LR1 here instead of chi-square. Okay, p chi-square. So chi-square p chi-square represents chi-square CDF. This is 1 degrees of freedom. Likelihood ratio test, present value, blah blah blah. So what test? So what are we testing? We have parameters, 2 parameters, for which one needs to be 0 and one needs to be 1. So beta 1 equals 1, beta equals 1 or not 1. All right, and we have we have 2 parameters here. And so the simplistic term 1 0 that we have seen in our theory part, and q equals 0 because there is no 1, nothing is 1 here. The direct value 1 is not there. R is creating a column with 1 0 and q is 0. Theta 1 is in column beta hat, first the beta hat value, then by variance beta hat 1 value, which is unrestricted beta hat divided by the variance of the unrestricted parameter. So column bind, then C. Okay, you have to do C and column bind both. So C beta hat sigma squared, then column bind. Great. Then we have I, information matrix, and where is it coming from? X transpose divided T sigma square 0 0 1 by 2 sigma square. Okay, so this is, just have a look here in the world statistics. What is, we have sigma square T 2 sigma square T in world statistics, right? So here T into sigma square, so basically here 1 by sigma square, 1 by 2 sigma square, 1 by sigma square, 1 divided by 2 sigma square. So X transpose X multiplied to X divided by T sigma square 0 0 1 by 2 sigma square, 1 by 2 into simply sigma square whole square, which is sigma to the power 4. Okay, all right, so that is what it is coming from. How do you do it in R? First comes X multiplied to X. Which one is the transpose? Why am I not defining transpose? There must be a transpose, there must be an error here. X, anyway, X transpose multiplied to X divided by T. This is division, this is not, well, regression. T sigma square, regression was linear, called with linear model. Linear model, Y dependent, X independent, -1 $sign, this is the coefficient. My god, it's quite big. Where it is sigma square, then 0, then 0. Well, because I'm doing this in columns, so column bind is working here, is under work here. First put everything in a linear index in column, then do matrix, it will create a 2 by 2 matrix. That's the idea. Okay, then 0, then 1 by 2 sigma square, and I need 2 rows here. Okay, in the matrix I'm creating a matrix on these thing. I want a matrix with 2 rows, 2 by 2, that's all. Word test T r theta minus q inverse, this is already we know word test. R theta minus q inverse of Ri R transpose R theta minus q. So T multiplied to R theta 1 minus q inverse of R. So percentage into R theta minus q. I see in R we might not need to put transpose because it will automatically use, if there are two same thing multiplied in a matrix form, it will automatically consider one as the transposed one. Good, if that is the case. Percentage, any multiplication or division signs or anything will come within percentage signs if you are multiplying two matrices or two vectors. T is a vector, but there is no percentage sign coming in because this is not a matrix, I guess. So R multiplied to theta 1 because they might be different sized. Inverse of R I R, you see, R theta minus q, and chi-square distribution is 1 degrees of freedom, p chi-square 1 degree of freedom. So we have world statistics, then Lagrange multiplier GI. Okay, so let's get back to the game. What do we have in Lagrange multiplier? We have yt minus mu by sigma square, and then 1 by 2 sigma square plus 1 by 2 sigma to the power 4 y minus mu. This is all gradient matrix, isn't it? Let's see. Yeah, what do we have here? Have a look. First, y minus mu sigma square divided by sigma square. X is as usual there. Y minus x beta hat divided by t sigma square, because the distribution is different now. We have beta xt, and then the next one line is 1 by 2 sigma square. I'm sorry, got cold a bit. This is all restricted. 1 by 2 sigma square 2t y minus t summation of 2 sigma square okay, t y minus mu 2 summation of y minus x beta hat, not, instead of mu we are putting the value of mu y minus beta naught x square. That's all. Whole square y minus beta mu is equal to beta x. That's all. And information matrix is x transpose by 2 sigma square 2 by sigma square. So this is it. And information matrix is 1 by sigma square 1 by 2 sigma to the power 4. Okay, let's look into R. G is equal to, first column bind x multiplied 2 by 2 sigma square and multiplies just this scalar. This is a scalar. There is no percentage between scalar multiplications, so no problem, plus. But there is vector multiplications, there is a percentage sign. Information matrix. Okay, this was just a vector, now this is a matrix. Okay, so first do column bind, then create a matrix with your requirement. You need 2 rows. Then Lagrange multiplier is T into G transpose inverse of I into G transpose, and probability value is chi-square distribution function. That is for the first problem solved. Now this problem is in regards to Weibull distribution, where the problem is we need to generate 20 observations from a Weibull distribution with theta is equal to alpha 1 beta 2, compute the unrestricted maximum likelihood estimates theta 1 hat. A special case of the Weibull distribution is the exponential distribution when beta equals 1. Compute restricted maximum likelihood estimates when beta equals 1, and theta naught is equal to alpha naught and beta naught is equal to 1. Test hypothesis when beta equals 1, alternative beta is not equal 1. Test hypothesis when beta equal 2, alternative when beta not equal 2, using LR-Walt and LM test. Now there are local functions in Weibull distribution that I told to check first. In difference between Matlab and R in this case is that in Matlab we need to specify the local functions at the end of the total program, while in R we can do it in the beginning. Okay, so first pass the oh, by the way, this is the mathematics that you will be needing for this. So first part is to pass it as a function, then clear, as we are already familiar with this. Remove object, list is all, you clear all. Then set seed, global stream will be here instead of default stream, as I'm saying again and again. 13 Marcena twister and then sorry, function, create a function called inverse and return solve, which will solve with inverse. That's all. And let's start with the local functions. The first local function is unrestricted likelihood function, which is log L is equal to log LU. We are gonna well, we want it to give us output B and Y. No, we'll input beta and Y, and we'll have output mean of log L to beta Y. at each observation, this is just taking the mean of log likelihood function. Now log likelihood function at unconstrained or in unrestricted case, we pass in beta and y, where alpha is beta 1 and beta is beta 2, and log likelihood function is log of alpha, log of beta, beta 1 multiplied to log of y, alpha y. Okay, how this is coming? Simple. Log of alpha plus log of beta, unrestricted case, plus beta hat minus 1 sorry, mean of log of yt minus mean of alpha 1 yt. Okay, beta 1 log of y alpha y into beta alpha into y to the power beta, alpha into y to the power beta, alpha into y to the power beta, log of y. Okay, and then in this case we needed to return log 1. Easy, we needed to return log 1. This function will be given b and y, and it will return log 1. This function will be given beta and y when I call this function, and it will return lt. I can just call with lt, that's all. Constrained log likelihood function. So this function log lc will be given beta and y, mean of lc log 1 will return log 1. This function will be given, here is constrained because unconstrained we have alpha is equal to beta 1, beta alpha and beta both. We had alpha and beta both. Now in a constrained case we don't have beta. Great, see, we don't have beta or sorry, the other way around, we don't have alpha. Yeah, here because this is a different example. When there was alpha, we're interested, oh no, beta is equal to 1. We don't put in alpha, beta is equal to 1. We are actually constraining beta to be having the only value 1, nothing else. We have everything, but we're constraining beta to have a exact same value. So if there is beta 2, beta 3, just constrain with, okay, return lt, that's all. This is the local functions that we can use for optimization. So now we are creating the function. First 20 simulations, alpha and beta is given to us, 1 and 2. We're gonna generate Weibull random numbers. So you see in Matlab WBL R&D, Weibull random numbers, alpha, beta, t rows, 1 column. Weibull random numbers, R Weibull is special as R Weibull. Shape, scale, see, n, it already gives you a hint, n, number of observations t, shape and scale equals 1. Shape is beta, it will take the beta's shape because beta is the slope, so shape of the slope. And scale is 1 by alpha squared 1 by beta, 1 by alpha squared 1 by beta, because this is Weibull distribution. So 1 by alpha squared 1 by beta exponential, you see, 1 by alpha squared 1 by beta. Okay, very simple, just remember that. Sorry, to the power 1 by alpha to the power 1 by beta. Weibull distribution, 1 by alpha to the power 1 by beta. So we start initial value This is optimization. We're gonna start optimization now. In case of optimization, we always call the functions that we created locally. C alpha beta options optimset, display of large scale of optims results optimset optim initial value. Okay, we don't have to create an options here. For R, beta u and log L1 will be given by our maximum likelihood estimation by minimizing, which is I want the first the parameter beta at parameter beta. Beta start is the initial value. Beta start unrestricted function will run log lu by. We're just calling for log lu. Y equals y beta start initialize, calling the function normal distribution. Y equals y method is bfgs. So for bfgs we are actually using quasi-Newton method, or yeah, Burden, Fletcher, Golfer, Shano suggested BFGS method or the quasi-Newton method here. And the things that we pass in are first initial value par at par, or the initial value as the function, and y equals y is a function to return the gradient, the method to be used. So basically function to return the gradient, y equals y. The distribution is y equals y. And bu will have the results at par. I mean, when you run it, from the results the column par will be passed in bu, whatever the par or yeah, beta estimations. So the from initial the beta estimations are located in par, and the value is located in value, and in log likelihood function from results we will pass the value. Just remember that. And this is how we display it. Very simple. Log LT, log L1. Constraint estimation again is very simple. First, we have already for Matlab created options optimized large scale display. So again here in this case optim beta is constraint. So you see initial value is 1, we initialize with 1. Log LC yy is the par value, and method is quasi-Newton method. Options, okay, options is something that is not needed in R. So par, and that's all. And then likelihood ratio test, we have already the estimates from restricted and unrestricted. So this is the likelihood ratio test, and this is the chi-square. Then comes the wall test. Wall test is Hessian. For wall test you need the Hessian. So num Hessian from these that you have the parameters that you have estimated, the function, the parameter and the distribution. The function, the parameter and the distribution num has same, exactly same. Great. Then we are creating that, and then wall test for restrictions 0 and 1, and q equals 1 because there is specific value 1 in our parameter beta. We are testing beta against 1, so beta minus 1 equals 0, so q equals 1. Simple. Alpha beta, there is nothing we are testing for alpha, we are just testing for beta. So 0 1 t r into b beta, r beta minus q transpose r beta minus q transpose, this must be here. So r theta minus q transpose r theta minus q As you can see, there is nothing to do with the transpose here. T multiplied to column bind, we need to do column bind R beta minus Q inverse R H R transpose column bind. Okay, so column bind R, that's all. Instead of R transpose, R beta minus Q is the same thing. No transpose is necessary to us, it will automatically convert things to columns. So column bind W it as numeric. Okay, we want the results to be numeric. Not we want to avoid any non-numeric results. As numeric. Okay, great, fine. And then the same thing. Then comes Lagrange multiplier test. Theta naught is equal to beta naught and 1. Then gradient matrix is generated from numeric gradient. Okay, let's see Lagrange multiplier. Lagrange multiplier, you see, numeric gradient is generated from the gradient matrix is generated from numeric gradient function. Mean of, so G is mean of gradient matrix, J is Gmat slash T. Applied to gradient matrix divided by T. Matrix gradient matrix divided by T. So gradient divided by T. Alright, so gradient divided by T is J. Simply gradient and gradient inverse gives you the covariance, which is omega. See, covariance omega, so which is gradient multiplied to inverse of gradient. Transpose of gradient divided T gives you J. Outer product gradient. Okay, and then Lagrange multiplier T into gradient and gradient transpose. Mean and the variance, inverse of J. Lagrange multiplier test, that's all. Very simple. So before we do all the tests, we just had to call our optimization. We did optimization to estimate parameters for constant and unconstrained case. That is something interesting and new. That's all. Problem 3 is almost the same as problem 2. Instead of using anything, we are just using a gamma model. I have already told you before that gamma model will be in use. So this is a practical situation. We have daily $70 euro dollar data from June 1, 1973 to 25 February 1995. There is a total of 5,505 observations. The stationary distribution of interest rate R is assumed to have gamma distribution from previous chapter. Stationary distribution R is assumed to have a gamma distribution. Degrees of freedom, nu and omega is the variance. So you see omega nu divided by the gamma function, gamma of nu r nu minus 1 exponential of minus omega rt, where tau is the gamma function and theta, nu and omega are unknown parameters. Compute the maximum likelihood estimates of nu and omega and the Hessian. The mean of the gamma distribution is given by mu, which is nu divided by omega. Use the results from part A to compute mu hat. So basically we have to compute mu hat and standard error. Great. And we need to do perform a wall test. The variance of the gamma distribution is given by nu divided by omega square. We need to calculate that too. So skewness of the gamma distribution is given by, so kurtosis. So you have to do all these skewness and kurtosis and everything. So okay, let's just jump in. So this is, again we'll start with what? Local function. Great. So the function we are creating is neglog vy. New is absolute the value of first parameter, omega is absolute value of the second parameter. This is the gamma equation. Gamma equation is coming from here. So what do you see? New into log. So we're taking log on our gamma equation, logarithm of gamma equation. Okay. So in our chapters we have already discussed gamma distribution. So new log omega, when we are doing logarithm, new log omega fine minus gamma ln multiplied to new gamma ln multiplied to new, that is gamma log function multiplied to new in the denominator, as you can see, plus new minus 1. Okay, so new minus 1 coming up forward multiplied to log y. Okay, multiplied to log y, which is represented by r here, and omega multiplied to y, omega multiplied to y. So instead of r we are putting y. So very simple, we are just taking logarithm of that function and minus. So first we neglog. In neglog we pass in, we ourselves pass in the inputs by function. So new omega absolute b1 b2 elements are presented with third bracket, new into log m minus gamma log multiplied to new. Now gamma log is a function here already presented, where gamma that is already given in Matlab. Now here, for example, see, so related to the beta and gamma functions. So this is already given in R, so gamma ln is also given in Matlab. Gamma ln new minus 1 log y, and then that the function is created. Fine. Okay, and then comes the magic part. Because the function already created, we can optimize it as we wish. So test, load the data, return euro data column 4, test and test function. So here, this for inverse function we need to include this library, and yeah, hey, we didn't include solve. Okay, might not be necessary. So we're loading the data, then all rows column 4. See, in the element you don't have to pass in the dots here, which represents all rows. It automatically understands, so you just have to position the commas, that's all, in the third bracket. And length of r, estimate the model, where the starting initial, we initialize our values with 1. Optim, you see, we don't need this for in our optim set, large scale of display. So we need beta and Hessian with the function minimizing. So parameter neglog, the total function, starting value, and options, default option command. Optim, we initial par or the starting value, then the function or neglog, then our dependent variable, which is y. Here y equals r, so we are passing whatever r is in y, and then we want Hessian to be true because we want Hessian values. You see, great, very simple. Beta hat is the par value goes in beta hat, Hessian goes in here. So already estimated this. So variance covariance matrix is inverse of Hessian divided by T. So Hessian gives us, remember, Hessian gives us a square matrix. Hessian is important whenever we are doing standard errors. Beta hat 1, beta hat 2, calculated them, then we are presenting get concatenate and print. With concatenate and print, and you see you start with /n all the time. Common scenario. Estimate the mean and the standard errors. Mu is equal to nu divided by omega, that we already know. D is equal to 1 by omega. Okay. And D is equal to mu is equal to nu divided by omega. On the other hand, D is equal to 1 by omega and minus nu by omega square. See column bind. Okay, minus, this is coming from earlier chapters actually. So D is equal to, just remember, 1 by omega and alright, and minus nu by omega square, nu by omega. Okay, very simple. And then VR, the mean. This is the mean, this is variance, square root of VR. Okay, no, this is not variance, this is just, we need that for standard error. D, variance covariance, D transpose. What are we doing here? D, variance covariance, D transpose. Same thing, square root of VR with gamma function. Gamma, this is how it is presented. Great. Then we are displaying, then word test is mu q is equal to 0.1. Q is equal to 0.1. So mu q is equal to 0.1. Okay, given a specific value is given for q. Q is equal to 0.1, word test D, C minus Q inverse D, C minus Q. Okay, because this is non-linear, remember, not R minus Q, that will be C theta minus Q. Alright, so if you just have a look here, non-linear, C theta minus Q. Okay, C minus Q inverse of D, D Hessian, C minus Q transpose. We are doing transpose here. Good, but have we estimated the value of C? Yeah, C equals mu itself, so fine. Estimate the mean and the standard error. Estimate the variance and the standard error. Nu by omega square. So 1 by omega nu minus nu by omega square. So 1 by omega square minus 2 into nu by omega cube. 1 by omega square minus 2 into nu by omega cube. Just remember this, 1 by omega square. So 1 by omega minus nu by omega square. 1 by omega square minus 2 into nu by omega cube. Great. DVC, everything else remains same. Word test again 0.001, 0.1. Okay, just twist it a little bit. Sigma square is equal to omega minus mu. Oh ho, 1 by mu, 1 by omega square. Okay, 0.001. So with that, then skewness, for skewness is 2 by root over mu, 2 by square root nu, 2 by square root c is equal to k3, 2 by square root nu, 1 by nu 3 by 2, 1 by nu to the power 3 by 2, and then 1 by nu to the power 1 by nu to the power 3 by 2, 0, minus 1 by nu to the power 3 by 2, 0. These are the equations only. K3, okay, and square root. This remains same. See, these two lines remain same. It depends on how do you, I mean, every time the Q and basically this one changes, that's all. D remains same. Oh, okay, word test of this Qness, same thing. Kurtosis is 6 nu cube square 0. Just memorize this stuff. Rest is same. Okay, so that ends one with gamma distribution. In gamma distribution, the tests actually had the same form, no change, is C minus Q because it's non-linear. The only thing that we need to remember is the diagonal elements. These are the diagonal elements of your variance covariance matrix. We just need to remember the diagonal elements and the actual variables like skewness, whichever represents skewness, or mean or variance. That's all. And then the rest, running the rest is quite easy. Okay, the fourth problem is simulating the distribution of the world statistics. So simulate the following multiple regression model 100,000 times with a sample size t is equal to 1000. So this is a multiple regression model: beta naught, beta 1 xt, beta 2 xt2, beta 3 x3t. ut is independent and identically distributed, 0 mean and sigma square variance, where the explanatory variables are, well, 0, 1 normal, this is normally distributed, x2, x3 is normally distributed, but uniform distribution for x1. So basically, which means that the values will remain between 0 and 1, which are fixed in repeated samples. Theta naught equals beta naught 1, beta 1 0, beta 2 0. So basically beta naught is bringing 1 to Q, and sigma square is 0.1. For each simulation, compute world test of the null hypothesis. Beta 1 is equal to 0, and compare the simulated distribution to the asymptotic distribution given by the chi-square distribution with 1 degrees of freedom. So we have to compare the simulated with the asymptotic distribution that is given by the chi-square distribution. Then compute world test of joint null hypothesis where beta 1 equals beta 2 equals 0. Very important, joint distribution. Compare simulated distribution with chi-square with 2 degrees of freedom, because there are 2 variables, so 2 degrees of freedom. And because there are 3 variables bringing into the joint hypothesis, 3 degrees of freedom. Repeat parts A to C for T equals 10 and 20, and compare the simulated finite sample distribution of the world statistics with asymptotic distribution given by chi-square. Let us see how this goes. Sorry. Okay, first create the local function. Local function theta y x1 x2 x3. Okay, these we pass in. Then comes m is theta 1 plus theta 2 x1 plus theta 3 x2. Everything is represented, all the coefficients are represented with theta, plus theta 4 x3, and s2, which is the variance, is absolute value of theta 5 in the equation that is given, sigma mu s2. So the log likelihood oh no, sorry, it's not that, it's the sigma square value, is sigma square. and mu is 0.5. Half log twice pi minus half log sigma square minus half y minus m. M is the whole equation, root squared divided by sigma square. Okay, m theta 1 elements are within the third bracket, theta 2 x1, theta 3, same thing, absolute theta 0.5 log twice pi minus m. Obviously we don't need this here in R, divided by s square. So compute finite. We don't need the finite one for now. Let's just have a look into this. Finite one is quite complicated. Helper. we need to remove everything, blah blah blah. Then we need to do, because we're gonna do a simulation, so we're gonna set seed, then inverse, and then we need to load. This is a typing error, came twice, that's fine, no problem. So there is beta naught 1. We are given the inputs here, giving the inputs and square root of sigma square. See, we need to replicate the thing 100,000 times for t is equal to 1000 simulations. Good. X1 is, see, random t1 because it's uniform distribution, locates between 0 and 1. So run if t, the normal distribution, x2 t1 x3 t1 squared, because x3 is squared, u1 squared, t squared, because we don't need 1, it automatically creates things in one column. Array is to hold results because we're gonna probably run a loop. So world distribution 1 zeros, number of draws, yeah, 100,000 rows, one column. Zeros is array 0. We are gonna create zeros. Column will be 100,000. Column will be 100,000 times in one column. 0 0 zeros. So we are creating a zeros function here, where there we will put in 0 values for 100,000 times in one column, zeros and draws. Then loop over replication. Oh, theta naught is column bind. Oh, this is a progress bar, you can simply not use it. It's fun. It shows you how your replication are going. Text progress bar, minimum 0, maximum n draws, style 3. Okay, theta naught is column bind. So first see beta naught, beta 1, beta 2, beta 3, sigma square, all are column bind. Use the column bind. Loop over replication. See, theta naught, this one and this one is same thing. Options, optimum set, large scale, we don't need that here because we're gonna call this many times. It's gonna take sometimes quite big program. I is equal to 1 to 100,000 for I in sequence of 100,000. You now just do the function. Number of u is residuals is created with random uniform distribution t1 multiplied to sigma, that y is equal to beta naught. We're calling in the function beta 1. We're creating the equation actually. Then here we are calling the function. See, fn in search, p neglog py, everything theta naught options. We don't need to do fn in arc. Fn inside automatically optimizes it. Theta naught par is the initial value par. Neglog is what we are calling from the function. Y equals y, x1 equals x. This is dependent and independent, all the variables that are coming in. Okay. And algorithm we are not passing it. I think we just want the default algorithm. Okay, so results, P will have the initial results or the theta results, everything theta results, because in theta results we have beta naught, beta 1, beta 2, beta 3, everything calculated together. H is Hessian, numeric Hessian, neg log, first the function, then theta, then y, x, everything. So theta will have P, covariance will have inverse of Hessian. Great. So with one restriction, is okay, this is 0, beta 1 first with beta 1, then with beta 2, beta naught we don't do anything with beta naught, beta 1, beta 2, beta 3 is our constant. So beta 1, beta 2, beta 3, sigma square, isn't it? Yeah, have a look though. Mu, beta 1, beta 3, beta 3, mu. So C column bind, Q is equal to 0, world statistics, world test distribution I, 100,000 times we'll have a distribution of world test, so it's kind of like a rolling sample. R theta minus Q transpose inverse R multiplied to covariance multiplied to R transpose inverse R, covariance transpose of R, multiplied to R theta minus Q. Two restrictions. So beta 1, now beta 2. C, first column, then column, row bind. Okay, we want this to be in rows. Alright, row bind. We want this to be in rows for ease of understanding. Okay, row bind. Fine with me. Row bind, and this is in columns, so column bind. Okay. The same thing coming again. 3 restrictions, beta 3. Same thing coming again, and then set text progress bar PBI ending close PB. We're closing the progress bar. This comes for progress bar, so it shows when it ends. Alright, fine with me. And then generating graph. Have a look, histogram. I think the R histogram is much easier compared to Matlab in this case. But yes, I'm giving you 15 seconds to go through the graph. Thank you. That was asymptotic distribution. Now we're gonna move to the next problem. Okay, this problem is concerned with simulating the size and the power of the word statistic. So test first, there are two problems. There is test size and then test power. I think they will be very much the same, but still let's have a look. Consider testing the hypothesis beta 1 is equal to 0, beta 1 is not equal to 0 in the exponential regression, where we use inverse of mu, exponential of minus y by mu, in which exponential of beta naught beta 1 x multiplied to x is IID n01, which is fixed in repeated samples. Theta naught is equal to beta naught is equal to 1, beta 1 equal to 0. Compute the sampling distribution of the word test by simulating the model under the null hypothesis 100,000 times, looping rolling sample, for increasing samples of size t, using the 0.05 critical value from the asymptotic distribution of test statistics. Compute the size of the test 2. So compute the size of asymptotic test Also compute the critical value from the simulated distribution corresponding to the simulated size. Interpret results, compute the power of the voltage for increasing sample size with fixed beta naught, interpret the results of the simulation. Let's just do the test size first. So again, we're gonna look into local functions. So unconstrained log likelihood function at each observation. So beta naught is equal to theta 1, beta 1 is equal to theta 2, mu is exponential of beta naught plus beta 1 x, log L is equal to minus log mu minus y by mu, minus log mu because u inverse minus y by mu, very simple. Beta naught, so theta, we are creating a function. Log LT is a function where we are putting in theta yx, beta naught, theta 1, beta 1, theta 2, mu minus 1 by mu. Unconstrained log likelihood function total, just is this is the simply the mean, we're taking the mean of it, that's all. Okay, to create remove complications, we do it twice. Then Hessian, analytic Hessian. Okay, function Hessian, we are creating a function Hessian theta yx, where beta naught is equal to theta 1, beta 1 is equal to theta 2, mu is equal to exponential of whatever I have given. H itself is 2, 2. First create a 2 by 2 matrix, zeros. Here array C0, C2 by 2. First sum of y by mu minus sum of y by mu is located here. Minus sum of x multiplied to y by mu located here. Here is also the same, so minus sum of y by mu minus sum of x divided by x multiplied to y by mu minus sum of x multiplied to y by mu minus sum of x square multiplied to y by mu. Very simple. Then return Hessian. Then comes the wrapper function, which is the inverse. Minus sum of x minus of x bar minus sum of, okay. Alright, you might be asking why y by mu and x square multiplied to y by mu and 4. So first y by mu, then the mean, and diagonally we have mean and the variance. So this is the variance, this is the mean, this is the regular 1, 2. So then comes inverse. Then let's look into the main problem. So random stream, easy, set seed. Now t, these are given values that I'm passing. World statistics is zeros, 100,000 times 1 row, arrays 0, C, end rows 1 row. Chi-square is chi-square inverse of 0.95 and 1 degrees of freedom. Chi-square is q chi-square. Q chi-square meaning q chi-square, the non-central chi-square distribution. This is the non-central chi-square distribution, density distribution, quantile and random generation for the chi-square distribution, degrees of freedom and optional non-centrality parameter. So non-central chi-square distribution, okay, fine. I think this is given in the question. The asymptotic distribution, the test has to compute the size of test as simulated distribution. This is simulation, so you are using non-centered in case of simulation. All right. Then output is zeros to length of t, size output 1, size of the distribution and cumulative value of the distribution located in output 2. Okay, R names table array to store the results. Sample t size, critical value. Sample t size, critical value, all in second commas. So column names, replicate all 2 times. Replicate all 2 times. So what are we storing? Array is dimension, bind is r names, c names, these are, oh okay, link t will be replicated twice, c names, dimension names, list, r names, c names. So this, the whole thing is creating a table, that's all. We don't need a table for this. For I is equal to 100,000 times, for I is equal to sequence t, j is equal to 0, x is exponent variable fixed in repeated samples, random number t11, t1. For I is equal to main do loop to generate Monte Carlo results. This is length of t. This is 100,000 times. This is total t. 1, 2, 3, 4, 4, only 4. This is 100,000 times. Okay, we are creating a progress bar. Fine. We have exponential, mean, mu random, y, mu into log 1 minus u. Okay, mu into log 1 minus u, mu into log of y minus u. Okay, theta naught, initial is initializing, then initializing this thing, then calling option initial one, then the function of theta. Function of theta was created earlier. No, why am I asking log L theta yx, log L theta yx? Exactly, already created function. That was not okay, it's making a joke. Theta log L theta yx, or simply call log L method vfgs. Hessian, theta is results bar, Hessian is the function analytic Hessian, theta yx. Running that. Function theta log L theta yx. That's not necessary. This is another way to do it. That's all. Log L theta yx and passing that in function so that it looks a lot like Matlab. That's why, because log L theta yx is how Matlab call is. You write it down, then put it all in function of theta. That's all. One restriction, 0, 1, 0. Everything else remains same if world distribution is greater than chi-square distribution. Then we will, until this runs, we will stop it. J is equal to j plus 1, j plus I. So it will run j times, but okay, it's like it will go on. So if this we will continue until it's not, so until convergence. So until j world distribution is greater than chi-square distribution, will continue. When it's not, then it will not continue anymore. If it progress, this was not that important, you see. And size. So then we have size in the table. J by size is t, how many times it took for them to converge, j by 1000 sort. So 5, 10, 2500. Pre-interest. This table has already been created here. Here. This table has been created. Dimension, first array dimension is, dimension names are also given. Then it will continue until Weibull distribution is not greater than chi-square anymore. Very important and interesting program. Okay. See, one tweak is this. We can call the function in a different way, and I rows one column, exactly the same. Functions remain the same. Okay. So we checked for the size until the size converges, and at the end of convergence we want our system to show what was the size of our distribution when it converged, when the simulation became equal to the actual distribution. Let's look into power now. Power is also same. Again here, let's look into the local functions. We create the same local function. We create this exact same local functions. Unconstrained log likelihood defined, where Hessian defined as the same, and then let's use it in the problem. The problem begins here, where you see it's all same. Number 100,000 draws, zeros and draws, because we are gonna create, we need to store things. Beta 1 range, because in our problem we had this range thing. We want to actually see when it converges. Basically, let's see if there's in the book. Yeah, we want to see with the power of our test by construction of the power size adjusted. The size adjusted power of the test increases monotonically as the value of the parameter moves further away from its value. Under the null hypothesis, the maximum power of 99% at beta 1 equals plus minus 4. An important property of any test is that as the sample increases, the probability of rejecting the null when it is false or the power of test approaches unity in limit, becoming a consistent test as sample increases. So you need to prove that they're reaching 1 at the end, which means the test is consistent. That's all. So we'll start from -4 to 4, and we'll see if at the end we are reaching 1. Power is zeros, 1 rows up to column this. 100,000 replication distribution, zeros, replicate 0. K. In K, first we'll start with the smaller range. First we go by rows, man. First we go by rows, then we go by columns. First we go by rows. Beta 1 equals range K, which is simply going by rows. J is equal to 0, X random number T1, same, R norm. Then by columns, 1 to sequence of n draws. And then you put in everything that you have learned, the equations, random T1, not random number, uniform distribution, mu log 1, theta naught, beta 1, theta naught function of theta. Method is VFGS. Previously, did we use the method? Method where, yeah, numeric. Quasi-Newton method, we use quasi-Newton. Theta power Hessian, one restriction. Okay, fine. If is greater than 4.28 up until it reaches greater than 4.2, keep running, and when it reaches 4.2, the world distribution, the highest value of the world distribution, then stop it and tell me the power of the rows at that point. J by n rows. J is starts with 0. J basically starts from 0. J starts from 0. This is the initial J value. So that is it. So I'm gonna draw a conclusion in revising this chapter. There are one more problem, but that is quite big and I don't want to go through it now, and I don't think that is gonna actually restrict us applying anything that we learned and solve our regular day-to-day problems. Whenever we're trying to check for significance on the parameters, we have learned enough. I think most importantly what we have learned is that not only with different distributions how we can check for with different testing methods like LR, world and LM, how we can check for significance, but also we have learned the important relationship between these three significance testing, where all of them asymptotically converges, all of their values asymptotically converges to world test. So world test, whatever value world test produces when t tends to infinity, LM and LR test produces same results. That is what we have learned. Another important thing is that we learned that world test can be used finally for joint significance test, which is essential for testing our models. And finally we also checked that we can create the distribution world test and LM test with the world test distributions, the results, with a loop function like maybe 100,000 times. Okay, so we can replicate the distribution if we are using simulation 100,000 times, and we are seeing if the simulation converges to regular normal distribution. And when the simulation converges, the power of test, we have proved that as sample increases, the power of test and the size of test both becomes consistent and strong. This simulation with a huge replication means a lot. Like, it's not only giving you a significance on your model, that with simulated data, simulating distribution for a long time over a huge simulation, your data that is not real data, simulated data, gives you same distribution as the real data. So basically that actually allows you to check if your model is applicable without using real data. And that's a very good method. In the last two things we learned, there's much more to learn in simulation, and I'm just primary stage. Over time I think I'll be better. And that was a very important chapter, hypothesis testing, going on for like 4 hours now. So goodbye, tata, and thank you very much for your patience.